My name is William Falcon. I am a PhD student at NYU and Facebook AI Research. So I'm working on unsupervised representation learning, which means basically trying to devise some sort of learning technique to try to extract more information from data without labels, so that you can use this for like downstream tasks and get better accuracy or whatever you're trying to do. So this is an active field of research. So what I'm showing you is basically us bridging the gap between unsupervised and supervised learning, or like getting closer. We're not quite there yet, but I'll show you where the gaps are. So if you wanted to apply this in industry, what you could take right now. I mean, Bert's like pretty popular, most people know that, but that's one instantiation of this. So today I'm going to talk about the difference between these three concepts. There's unsupervised learning, self-supervised. There's unsupervised learning, self-supervised learning, and self-supervised, sorry. Unsupervised, self-supervised, supervised. There's active learning, there's semi-supervised. There's these other things which I'll kind of cover a bit. But it mostly has to do with how many labels you're using or, yeah. Next, I'm going to tell you why we don't want to be doing supervised learning generally. This is more like a kind of existential reason. Costs of supervised learning. So this is more, I'm trying to tie it more to like why would this cost you as a company a lot of money? I mean, I think most people know the reason. And then theoretical approaches. So I'm going to do a little bit literature review, and then I'll go into kind of the main two state-of-the-art methods, and then go into my own work, which we're publishing this week, and our results and like how that works. And then cover the current state-of-the-art. So again, the things that we're working on are general methods that can apply across computer vision, natural language processing. They're more like theoretical developments, but we test a lot of them in computer vision because it's easier to understand how they work. But you could extrapolate those to NLP. And then some closing thoughts, just like a very quick summary. Okay, so the main differences: unsupervised, supervised, and self-supervised learning. Okay, so I want to take a vote. Just people, you can just shout what you think this is. Just tell me, what is this data point? What is it? Dog? Okay. What about now? It's a what? Dancing dog, okay. Anyone had something different? Yeah, child in a costume. I could see that, like a toddler, yeah. What else? A begging dog? Okay. Cute dog, yeah, that's like the first one that people say. Cutest thing ever, right? And then you have dog, then you have dancing dog, pet in the living room. So I went around fair and took a survey, and this is what people said. Pet on the floor, dog evolving. So the point is that humans are biased, right? So when we're labeling data, we're embedding those biases into that. So when you have labeled data and you're running it through your systems, you're bringing that in implicitly, which means that you are not necessarily going to extract the relevant information. Maybe for your task, you think you need the class of the object to solve that problem, but in fact you don't. Maybe you need the relative relationship of how the objects interact with each other, or how physics plays a role into the task, right? But you won't know that if you're labeling data on your own. So this is like the existential part, why we want to generally move away from supervised learning. So one thing that people know about, I guess, is transfer learning. And I'll just motivate what this means. So why do we care about a good representation? Before I came to NYU, I was here at Columbia doing neuroscience research. And we were basically looking at neural activity in the brain and the retina, and then reconstructing things like images or maybe movement from that stuff. However, when we were collecting this data, it's really expensive. So we would have to wait for like an animal to either pass away or something, and then measure some neural activity for like an hour, and then that's all you had. Maybe that happened every 3 months. And so we would flash ImageNet on like a monkey retina, and then capture the neural activity, and then reconstruct that image later on. So that's some work we presented at NeurIPS a few years ago. And the problem is that, I only have maybe like 2,000 samples of that. So I can't really do that well unless I have a really good prior model, which is a representation extractor. Another case is medical imaging. So you want to do cancer detection. There are not a lot of those images. And so you would need a really strong model, something like a VGG-net, pre-trained on ImageNet, which you would use to extract features and then do some classification on. And self-driving cars. So another thing here is, a good example is you see kids here, whatever, but in the real world, a helicopter might fly through there. So your data is not going to capture that information if this is what you're looking for, humans and those kind of labels. So you also need a way to model this kind of like uncertainty about the world. So what is the cost to this, right? The first thing is obviously there's an accuracy cost. So if you have supervised learning versus weakly supervised or unsupervised learning, you basically, this is kind of the curve in terms of how much it's going to cost you to get these labels, right? So right now, you can get really good accuracy, but it's going to cost you a lot of money to get these labels. Unsupervised learning, there's a ton of unlabeled data in the world. So what we want to do is shift that and basically say, cool, if we could extract better representations, we'd be able to use all of the videos in the world, all of the images, to extract all the meaningful information. So this is generally what we want to move. There's a big economical impact as well for companies. So unsupervised learning versus self-supervised learning. In self-supervised learning, this is one example. This is something called colorful image colorization. So you have an image that you desaturate and you just turn into black and white. And your task is to basically come up with some model that puts that color back into the image, right? So this is called self-supervised learning because you're taking something in your input and trying to predict a different part of it. So you could chop this image in half. In this case, you're taking the color channels and trying to predict the other color channels from the non-existing color channels. This work is about solving a jigsaw puzzle. So let's say you take this picture of this tiger, I guess. I don't know what this is. And you overlay this kind of grid of like a jigsaw game. And then the task is you basically shuffle these and you try to get your neural network to solve that task. And so this kind of works okay. But again, two things that I want you to notice is that you have to know that you're dealing with images to do any of these things, right? This won't generalize to NLP because I can't jigsaw a word, for example. So you need a lot of domain knowledge. So these things rely a lot on the data augmentation stuff, not necessarily in the learning algorithm. So we want to build intelligent systems that generalize well. We don't want them to take information from that specific domain or need information from that specific domain to solve the task. The third kind of work is very related. So this one, you have some context. And here you might have a photo of a cat. And you basically randomly pick two patches out of that, and you say, well, here's a question. You have two questions at the bottom. It's basically like an analogy. You would say, well, in question one, the wheel. What's a relative relationship between the wheel and the express symbol there? When I'm giving you this cat, so would that match to like an ear and a nose? Could you solve that task? So this is okay. All of this work is from like 2016, 2017, so a few years ago. And this one is about predicting image rotations. So you take an image, you rotate it, and then you have a softmax over the angles that you rotated. So you could have 45, 90, whatever, and then you try to predict which one it was. Again, all of this stuff is very specific to images, so it's not something that we want to be kind of moving forward with. So now to just kind of highlight the point that these things should be general across domains. We have Bert, right? So Bert is another instance of representation learning where you have this mask word prediction task, and then you have this next sentence prediction task, right? So I love AI because it's crazy that it works. So these two tasks define kind of the Bert training model. But again, this is a bit domain specific. You need sentences, you need to be predicting the next sentence. Although I argue it's kind of general because I could think about this as a video as well, or a sound sequence. It'd be the same concept, where I would mask parts of it, try to predict the other parts from the context, or try to predict the sequence from the previous sequence. So I think everyone's aware, but Bert's kind of, well, there's a bunch of other work on top of it now, but transformer-based networks are the state of the art right now for NLP, transfer learning. And you can see that whatever the tasks are doing under the hood, whatever the representation that you're learning under the hood allows you to fine-tune on a very tiny data set and get really high accuracy. This is another work. This is unsupervised machine translation. A lot of this is from FAIR and also my advisor at NYU. So what you do basically is this purple and blue They're like languages, basically. Sorry, we'll do this animation again. Okay, so on the left and the right, you have purple and blue. You could be like Spanish and English. And in the red, in the middle, you have this like latent language that you don't know what it is. And what you're basically doing is you're saying, cool, if I can rotate these two languages into a single shared space, and I know some of the words map, then I'm going to assume that the other mappings will work. So in this case, you have gato and cat, and then in the other language, in that space, you'll be able to just pull out that vector around that kind of like location and latent space, and that normally gives you like the translation. So this is unsupervised translation, meaning I don't need to have like so many examples of a sentence matching the other sentence, right? So they do a really cool job. This is 2017 as well. They've expanded a lot more now, but you could think about this, like the implications of this are really interesting because you could take something like a language, there are a lot of countries in either Africa or Latin America where you have a lot of natives and they have different dialects and things that will never be translated. So you can think about this as a way to do that, to bridge that gap. You maybe take a few texts that they have and you're able to do this unsupervised translation part. So I'm explaining these things because I want you guys to think about, I guess, all of this in like very abstract terms. Like I said, this happens to be text, but you could think about this as sound, you could think about this as images, videos, whatever you want. Just the core idea is what's important. So again, why is this bad? Well, I already motivated the first reason, which is we need too much information, too much domain expertise to solve the task. But I'm coming at it from a neuroscience perspective as well. And a lot, like we want to motivate a lot of our work, at least in my lab, through how we think humans learn. And so, when you're an infant, the kind of main thing is, let's say that, so when you're an infant and you kind of develop your sense of vision, the first thing you see is just a bunch of blurry pixels. You don't see any shapes or anything. As the time goes on, you start sharpening those pixels into actual objects. You start clustering them into objects. You add color back in, and then eventually have a full clear picture. So one of the things that motivates kind of our research is, if this blurry image never moved, it would be really hard to separate what objects cluster to what. So one thing that we're looking at is videos, right? So humans, like we really should be looking at some sort of sequence so that we can track information over time, how motion changes. Through doing that, So through doing that, we're able to extract things like, maybe humans, there's physics involved. If they hit a ball, the ball isn't going to disappear. It's going to be pushed away. If they eat something, it might disappear. So there are all these relationships that are not encoded in any kind of labels that we want to be extracting. This is really useful for something like self-driving cars, where you might want to predict the physics trajectory of an object or your car itself. So you can extract things like intuitive physics from here, object permanence, those kind of tasks. So this, I think everyone's super familiar with this. And this is basically an analogy for the bits of information. So a label mostly carries the number of classes as the bits of information that you can use to learn from, right? So that's supervised learning, the icing on the cake. And then, the cherry at the top, basically for reinforcement learning just means that you get a scalar reward after running some really long trial. Like you play a game for like 2 minutes and then you get a score. That's the only information that you're getting. Things have gotten more interesting where you can extract more information, but at the end of the day, you have a trajectory where that reward basically summarizes what happened. So it's very, very little information. However, in unsupervised learning, self-supervised, predictive, you have all of the information in the image. You have the way that the objects separate from each other, how they interact, the colors, so much information that we can take advantage of. So unsupervised learning, so that was self-supervised learning. And NMT should have been in this section as well. So when people think about unsupervised learning, maybe the first model to think about is this autoencoder model. So you have some input, you run it through some model, and then you try to reconstruct that input, right? So normally you would modify the input somehow. Either you add noise, you chop parts of it off, you remove something that makes it not easy to reconstruct. And then you have some sort of latent space that encodes latent variables that you can use to basically reconstruct that image, and hopefully they can give you things like disentanglement, right? So there's an NVIDIA paper where they could take one of these latent variables and kind of interpolate in that latent space, and it would change the color of the street of the reconstructed image because they were able to disentangle that part of it. So you could imagine you have 100 of these latent states, and if I were to change one of them, the eyes of this frog would change. And if I change the right combination, perhaps the face of the frog changes to something else. And so this is kind of this entanglement that we want to be doing under the hood. And these are all theories that we think that maybe to actually build intelligent systems, humans do disentangle information. Could be wrong. Maybe we don't actually need it. But right now, that's what we believe. I think everyone's familiar with GANs as well. So, you have an image, you have some generator that makes a fake image. And basically, the task is to have some other neural network decide whether the real image is actually a real image or the fake image is a fake image, right? And so you have this kind of like game theory game. And then through that, you reach this equilibrium where the generator should learn to match the distribution of real images. And so it can generate arbitrarily complex images that appear to be from the same distribution. And the discriminator should be very good at distinguishing something fake or not, but at the end, it should be very confused, because if your generator is good enough, then the discriminator will be tricked all the time. And so the point of this is that people have tried to use this for representation learning. So the generator, then they might use the generator to run an image through it, and then extract that feature map at the end, and then use it for like classification in some downstream task. It turns out to not work that well. Also, same for autoencoders. So you would take an image, take the latent state, and use that to classify something downrange. Okay, so this is the first. Now we're getting to our research. So this is the first work that I'll explain. It's learning representations by maximizing mutual information across views. This is from Mila, so Joshua Bengio's lab, and MSR, Microsoft Research. And you have this image, and basically it's like a 4-stage process, right? So you take this image, you run it through this data augmentation pipeline, and that pipeline gives you 2 versions of the same image. It's unsupervised, we don't have labels. So why we're doing this is because what we're saying is, hey, let's assume that every image is its own class. Like, we don't know how many classes there are, but we know that that image has to belong to a class because it is an image. So we're gonna say it is its own class. Now we're gonna somehow sample 2 versions of that. Now we have two samples from the same class, right? So we have this frog, even though it's augmentations, we have this like upside down green frog, and then we have this kind of blurry version of the frog. The actual augmentations are more complicated than this, but the general idea is that you take a single image that represents a class, and you sample 2 versions of that class by transforming that image. So now we have what you would call a label. Like, I can say, well, cool, I know that this image, that these 2 samples should be close together. Like, we want them to say that there should be as similar as possible. So you take each one of these guys and you run them through a convolutional network. That's going to give you 3 feature maps. So normally everyone works on just like that last feature map. In this case, we're taking 3 feature maps. And the CNN normally is a residual network. And then we use the same network to run the other image and extract those 3 feature maps, right? So now we have, for each image, remember, these feature maps represent that image. So 3 feature maps that describe what this image is about. This is where the across views part comes in. So they're saying across views means the kind of abstractions from F1, F2, and F3. F3 summarizes more of the image, F2 less of, like, it's more local, and F1 is much more local. So what they do now is something called negative sampling. But the first thing they do is they sample a single vector from, So they sample a single vector from that F3 of the first image, and they compare against all of the vectors in F2. So these are tensors, right? So the dimensions here for each one of these guys is batch by row, by height, by depth. And so you can think about the row and height as a number of vectors, and the depth as a dimension of that vector. And so you would pick basically an I and j, you sample randomly, pick one of those vectors. So if you had 64 channels, that vector would have 64 dimensions. And then on F2, you would take all of those. And then you do compute a dot product between all of them. And you call those your positive scores. So they do this task across 3 different feature maps. So they take the last feature map against the previous 2 of the other image, and then across the middle 2. And then they minimize the softmax of this. So what you're seeing here, again, is for this one image. But if you normally have a batch of data, so now because you assume that every single image is its own class, in that batch, you're going to take every other image that is not this image that we're looking at, and you're going to say they're from a different class. Even though there might be a few collisions from that same class, you're just going to ignore that. And you say all of these other images are from different classes. And so now you have these comparisons. This dot product between F3 and F2 gives you a positive score that you want to maximize. And then the dot product between the F3 red here and like, let's say a blue from a separate image, you want to minimize that score. And so you can put this into a softmax, and that's called contrast NCE loss. I forget what NCE stands for, but it basically learns to say, okay, well, push things together that are similar and push everything else far apart. And then you do this bidirectional thing. So you do it the other way as well. So that's AMDIM. That's the first kind of work that we're comparing. This is something from DeepMind. This is called CPC, Contrasted Predictive Coding. And the way this works is kind of the same thing. So you have this data augmentation pipeline, you have an image, but instead of splitting it into two images, they split it into patches, right? And so they calculate these overlapping patches. And you can think about each one of these patches, again, as representing a version of an image from that class of images, right? So parrots, there are 9 parrots here, but it's really just a one. So you take those patches, you run them through the encoder, and you get the Z tensor, right? So in this case, you had 9 patches. The Z would be 3 by 3 by number of channels that you have there. And then on the right, you have the super complicated prediction task, which is we find to be not necessary once we like look through our framework. So I'll explain this. I'm sorry for the naming, but this is what they use in their paper. And also DeepMind doesn't release their code, so I spent a lot of time implementing this. Anyways, so you have the Z. Remember, the Z is a vector that's 3 by 3 in this case. And sorry, it's a tensor. It's a 3 by 3 tensor with so many dimensions. And this black part of it, sorry, can I move here? No, I can't. Okay, there's this like little black square on that Z at the top. That's like a context window. So you could think about this as a convolution. So a single convolution over those vectors. And that's going to give you a summary. It's going to give you a single point that summarizes all of those 6 vectors. That's that blue output. It's applying that convolution over all the Z's combinations. You get another tensor. That's basically a summarized contextual version of all the Z vectors. Okay, so this context encoder, that convolution that we applied is a different neural network. And now you're going to say, okay, so I have, let's say that you treat the image as kind of time. That at the top left, you have time 0, and at the bottom right, you have time n. So you're just going to think about this as some sort of like time sequence. And you're going to say, okay, at time 0, so top left corner, I'm going to take that C that corresponds to that. I'm going to try to predict something at like time n or something way below that specific patch. And the way you do that prediction is you take the C, you multiply it by a weight matrix at that row that you're trying to predict. So you're saying, oh, I want to predict at time n. Then you take a W matrix at time n, you multiply by your C, and then now you have a label, right? Because that multiplication WC gives you like your X, and then the actual Z from the bottom of the left is going to give you the label, what you were trying to predict. And so now you're basically just minimizing that distance. So that's CPC. It's a little bit confusing, I know, I'm sorry. But implementation-wise, these W's on the right, they're actually like a list of matrices. So it's just like a bunch of linear layers. And anyway, so why we're going through all this trouble? Because we want to learn, again, representations, and we think that this is one good way to do this. This particular method, constructive predictive coding, is motivated by neuroscience as well, something that we do, which is called predictive coding. They loosely tie it to that. You know, a lot of these things are like very loosely inspired neuroscience. And then they become engineering challenges. Okay, so this is our work. This is what we're introducing in a few days. So basically, what I just showed you is kind of confusing, and there are like a lot of ways of doing this, right? And so we looked at all this work and basically tried to figure out what are they all really doing and what's really driving their performance. And we basically came up with a framework that you can summarize any algorithm that's doing self-supervised learning into 5 steps. So in this case, you have some sort of data, which is your X. That data is unlabeled, so that's number 1. That's like the first requirement for this framework. The second requirement is that you have some data augmentation pipeline. This is A of X. In AMDIM, that was splitting the two images. In CPC, that was creating the patches. Great. And then you have on the right, you have this, on that number 2, you have an encoder. So now you have the third ingredient in this framework is that you have some way to encode either of those transformations that you did and extract features out of it. Then number 4 is this APN sampling that we're talking about. So AMDIM had that weird like F3 to F2, F2 to F2, F3 to F1 sampling strategy. CPC basically did it through that C and Z network. It's the same thing. We're just generalizing that and saying, well, once you have these positive anchor and negative features, you want to somehow relate them, right? So the anchor and the positive were the two things from the same image, and the negative was all the other images that are not, or the features from all the other images. So we generalize it to that. And then the 5th ingredient is a loss function. You can do anything, metric learning, but it turns out that the softmax works the best, NCE loss. So the more negative samples you have, the better that these tend to do. So after analyzing all of that, we basically understood kind of where some of the issues that these algorithms were having, and we introduced our own version of these. So it's called PatchDim. So PatchDim basically takes the augmentation of AMDIM, which is you take an image, get 2 versions of that image, and then applies the one from CPC on top of it, where you patch it up, right? So it's just the 2 augmentation pipelines put together. But now we can simplify everything else. Everything else is super simple. So now you take an encoder, you encode these patches, and then you just have 2 feature maps, one for the top image, one for the bottom image. And our sampling is very straightforward. You pick one vector from image X1, and then all of the other vectors from image X2, you do dot product, compute those scores. You want to maximize the sum of those. And then you take a different image and you do the same thing, but you want to minimize the dot product between those. So our strategy is a lot simpler. So basically, what we find, so here I just want to summarize the kind of big high-level ideas where like the algorithms differ. Because if you read these papers, it would seem like they're all doing very different things, but they're all doing the same thing. So where do they differ? That dot product that I mentioned, that can be generalized to like a similarity function, some kernel. Everyone's using dot product, but you could use something else. You could use correlation, you could use whatever. Just some way to relate those 2 vectors together. The encoder, for all of us, we use ResNets. However, AMDIM specifically does not work well with any other ResNet, and we found that through our experimentation. Our method fixes that problem, so you're able to use any kind of ResNet, which is good because there's so many moving parts. The last thing you want to be doing is trying to figure out how many layers or like what the width or depth of this thing should be. So you can just take any arbitrary like ResNet 50, 100, whatever. The loss, everyone's using NCE. The only difference is CPC has like 3 sums of NCE loss instead of just the one, which is F3, F2, 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 F3, and F1. Each one of those is an NCE loss. And then the data augmentation pipeline, just summarize how we do it. So in AMDIM, you get X1 and X2 out of A of X, which is the two images sampled from the augmentation of X. CPC, you only have that one. And then in ours, again, you have 2 versions. How you draw the anchor positive and negative features is this way. So in AMDIM, you just, from that from that feature map, you pick one single vector, that's RA. For CPC, you do this projection with WK, CI, and then the plus K is because you're going forward in time, so K time steps, and then at the jth spot on the columns. And then you try to predict the Z vector, which is that red guy, at the offset by K. So it's at the same indexing, just across the 2 different maps, and that's your anchor feature. And then for ours, it's very simple. You just sample that one vector from that feature map, M1. I won't bore you with the other details, but basically positive features are sums, and then negative features are sums across all of the other images. So main takeaway is, from this, in a batch, you have a single image. You assume that image comes from a class, and you generate 2 versions of that image. You're going to calculate the similarity between those 2 and say that you want to make that high. And then for every other image in that batch, you're going to assume they're a different class, and you want to minimize that similarity. If you do this wrong, you're going to share too much information between the 2 images that are the same, and you're going to learn a trivial solution, and you're not going to learn anything. So what we find Yeah, sorry. Okay, cool. So the data augmentation pipeline basically is what we find that helps us not learn those trivial solutions. So how do we actually do performance-wise? The CFAR10, sorry, the ImageNet numbers are still running because it's a very long model, or a very, very big model. So on CFAR10, 10 classes, 100,000 images. Their reported results are 93. Our implementation of their paper is 92.1, so we're pretty close to getting whatever results they report. We think we're off because of like the seed or something. And then CPC doesn't actually work that well because they only ran the test on ImageNet, so we're finding that it's not necessarily working super well on like smaller images. However, it's very hard to reproduce our work, so there might be a bug in our implementation that basically doesn't close that gap. The second, and then our results are, we're basically pretty close to AMDIM. Again, this is, sometimes we get over, sometimes we get below, but this is on average. We're right there, just a little bit below on CFAR10. STL10, same thing. We actually do surpass them on the accuracy there. STL10 is an image, it's another data set, which is 10 classes, but you're given 100,000 unlabeled images and only 5,000 labeled images. And so we're getting these accuracies. Again, the way that we're reporting this is you take that data set, CFAR10, you drop all the labels, you pre-trained on that using these methods that I just explained, and then you converge, right? You freeze that model, and then you add labels back in slowly. In this case, we added all the labels because we're measuring something called separability. So we want to see how well that representation disentangles linear separability. And then we add all the labels back in, and then we fine-tune a 1024 unit MLP. So it's a very tiny classifier that is not powerful enough to solve this task. It's just to map the representation to the classes. And we find that we get these numbers, 92, 91. On ImageNet, we're in the low 60s. Yeah, so low 60s basically right now as it's continuing to train. So what are the main advantages? So we pretty much have the same performance. The first advantage is that you don't need this crazy sampling that AMDIM is doing. Instead, we can just do this, which is just the last two feature maps. And we tested this by doing ablations. So this 1, 2, 1, 3, 2, 2, that's F1, F2, F3, these combinations, and we tried different combinations. And we see that AMDIM really needs that specific ordering. So their accuracies collapse when we change what we're sampling. So it's pretty arbitrary, it seems, how they pick those. Ours is pretty robust. Doesn't matter how you sample. Again, another advantage that we have is our network is much better. So you can throw any network at this and the accuracy won't decrease as much. We do find that wider networks do work a lot better. So you increase the filters instead of 64 to like 3200, something like that. And they actually tend to do a lot better. So yeah, so these are the main two advantages. There are a bunch of other ones I won't cover on here, but we have fewer parameters. Our network trains a lot faster as well. So I mentioned that this stuff is very expensive to compute. And so, hold on. Okay. So basically how we do this is using this framework called PyTorch Lightning. It's a framework that I developed over the last year, mostly at NYU and FAIR. And basically what it does is it allows you to plug your code in and then get automatic like distributed training, half precision, all this other stuff. So just to illustrate, the ImageNet model that's training, right now it's training on 384 GPUs, and it's taken about 20 days so far. It has not converged yet. And these GPUs are V100s, 32 gigs of RAM. They're state of the art. But it's taken a lot of compute to do this. Yeah, oh, these lines are because sometimes you have to wait for other jobs because, the other people have to run stuff too. So this is just the main model, but you can imagine we do grid searches. I mean, at any one time, I might be running a few thousand GPUs for grid searches, that kind of stuff. So what is a big deal about this as well is that Lightning addresses the reproducibility crisis. So this is NeurIPS. This is a big AI conference. And they're using Lightning as their official framework to implement a lot of the papers, mainly because it works super well without you having to modify anything. And I'll explain what I mean by that. So this is a Lightning module. So you can think about this like a PyTorch module. How many people use PyTorch? Just raise your hands. Oh, wow. How many people use TensorFlow? How many people have not built any deep learning anything? All right, good. You guys can try this then. So here, this is just a classifier for like ImageNet. Basically, you just subclass this class, Lightning module. You define this is just a single layer network. So 28 by 28, image, net image, and you have 10 classes. The forward is just your forward pass, right? So you run the output through a ReLU, and then you calculate some classification. On the training step is what would go in the training loop. So normally, most things you have to code this training loop where you say for batch in dataset, for epoch in epochs, for batch in dataset, and then there's a bunch of stuff that goes in there. That's really what most people care about. Then there's a bunch of stuff about backward pass, optimizer step, like mixing, accumulating gradients, all this other stuff. Training step is what happens after for batch in dataset and before you take the optimizer step. So it's really the core of what you care about. And so in this case, this is a very simple model where you just run it through the forward, you get this output, and you run it through cross entropy, you get some loss, and then you just send that loss back into the system, and it does the optimization for you. You don't have to do anything. If you were to do something like translation, you could get arbitrarily complex on here. So this is a research tool, but you can use this for anything in industry as well. Everything I just showed you, I did using Lightning. It's all written on here, and it's used at FAIR a lot as well. So on this training step, for example, if you were doing translation, you would have like an encoder, you encode that, then you'd have a for loop for like beam search or some sort of decoding. So it's as arbitrarily complex as you want to make it. But for validation step, maybe you want to do something else. So here I just did a loss, but in validation, maybe I want to calculate, in this case I did loss as well, but I could do accuracy, or I could generate images, or I could do something, sample the outputs. So it's a very different part of the training loop. Then you pass in what optimizers you want to use. You could just pass in multiple if you want it, for example, for GANs. And then you define your data, where they're coming from as data loaders. This defines a full system, and this is all the code you need to do to run this stuff on 200 GPUs. So how does this work? Like if you look on this, you don't see anywhere that I'm calling CUDA. You don't see anywhere that I'm calling half precision or any of that. I'm not moving data around. What happens is when I instantiate that model, I init this trainer, and I call fit on it, and that's it. So if you wanted to specify a number of GPUs, you just set a flag, you say 10 GPUs for however many machines you want. And under the hood, it launches all the orchestration stuff for you. It assumes you have a Slurm cluster, but we're moving into AWS and a few other things as well. And then what do you get out of this? So literally these 3 lines of code and what I just showed you gives you automatic tensor board. You don't have to do anything. It's already built in. It also gives you automatic training loop, validation, checkpointing. So it's going to tell you when to save the weights, early stopping. And yeah, so that's basically how we do the scaling stuff. So in summary, unsupervised is state-of-the-art in NLP right now. So if you want to do anything with NLP, I would use whatever the latest model is. GPT-2, Bert, just look on the archive. Computer vision is lagging behind in that. I mean, you can do transfer learning by using pre-trained models on ImageNet, but we won't have the representational power of Bert. Like Bert changed everything because a lot of it is unlabeled, like it's unsupervised. That's like the main point. Until we get to that point in computer vision, we're still going to be lagging behind. Once we do, though, we're going to unlock new ways of using our data. So you're going to be able to do things that I can't even imagine right now because I'm like in this limited world of what we know so far. And main takeaway is that we need to move away from images, like domain-specific knowledge, and some of these clever tasks. Basically, from 2016 to 2017, the research was coming up with some cool tasks like solving a puzzle or rotating an image or something. It wasn't on developing an actual learning algorithm or a method for learning. It was on like these sort of tasks. And again, we find that on the state-of-the-art methods, including our own, most of the games come from the data processing, not learning. Which is why we're kind of moving away from that work now, because we just wanted to understand what was driving the advancements in that line of work. So that's it. Thank you.